Cutting solid steel is a chaotic, physically violent process. As the tool bites into the workpiece, it generates massive friction, extreme thermal modes, and an intense, unpredictable material resistance that pushes back against the machine. Yet modern industrial manufacturing requires the machine performing this violence to maintain a strict positional accuracy down to 0.0001 inches. This is achieved using a CNC, or computer numerical control machine. A CNC is a manufacturing device that relies on a rotating cutting tool to carve materials across multiple physical dimensions. This diagram shows the standard setup for mapping that physical space. The movement of the machine table is controlled along a horizontal plane using the X and Y axes, while the vertical position of the spinning tool is controlled along the Z axis. By calculating simultaneous movement across these three distinct planes, the machine can carve exact, complex, three-dimensional geometry. The question is, how heavy equipment, operating under massive physical strain, completely avoids drifting off its target coordinates? Extreme precision is not an inherent property of heavy metal casting. It is an engineered output, maintained by a strict, multi-layered electromechanical architecture. If we strip away the physical steel and the spinning motors, we are left with the digital intent, the raw part program data, commonly known as G-code. This block diagram illustrates the central intelligence responsible for that code, the Machine Control Unit, or MCU. The primary function of the MCU is ingesting the coded instructions fed to it by an external input device. During the decoding phase, the unit translates that static text into a continuous stream of actionable motion commands. To plot complex shapes, the MCU relies on interpolation. Interpolation is the computational process of generating the exact microscopic steps required to form continuous linear, circular, or helical paths between two programmed points. However, the MCU is strictly a data processor. It possesses no physical strength and cannot turn a single screw on its own. Digital code requires an amplification system to convert low-voltage electrical logic into sheer physical force. The first physical requirement of the machine is securely holding and rotating the cutting tool. This task falls to the spindle drive, typically mounted vertically on the Z-axis. High material removal rates demand massive amounts of mechanical power, along with infinitely variable speed control to optimize the cut for different types of alloys. The standard industry solution is the AC servomotor. An AC servomotor is an electric rotary actuator that uses alternating current and precise feedback to maintain strict control over angular position, velocity, and acceleration. To drive the motor, a servo drive amplifier acts as the critical bridge, taking the low-voltage logic from the MCU and augmenting it to meet the high-voltage demands of the hardware. Under load, this drive continuously calculates and delivers the exact electrical power required to maintain the target RPM, even as the cutter encounters heavy resistance. The spindle supplies the raw cutting power, but applying that torque without pinpoint spatial positioning will simply destroy the workpiece. That positional control is handled below the spindle, governing the movement of the X and Y slide tables. These tables are operated by the feed drives, which are responsible for pushing the raw material directly into the spinning cutter. Unlike the spindle rotor, which spins continuously in one direction, feed drives must be capable of rapid starts, abrupt stops, and instant reversals of direction. Because of this, feed drives require constant torque characteristics. They must instantly generate the necessary force to overcome both static friction and the active resistance of the cutting tool. This rapid, multi-directional capability enables a manufacturing process known as contouring. Contouring occurs when several feed drives work simultaneously across different axes, each continuously varying its speed to carve precise, complex curves into the metal. Modern AC feed drives are built specifically for this rapid response, utilizing low rotor inertia and a high torque-to-weight ratio to shift directions without hesitation. The positioning speed and accuracy of these feed drives strictly dictate the final quality and productivity of the entire machining operation. The feed motor does not move the table directly. It connects to a physical lead screw, which translates the motor's rotary motion into the linear motion of the slide table. Conventional square or trapezoidal threaded screws suffer from sliding friction, leading to a fatal mechanical flaw known as backlash. Backlash is the microscopic physical gap, or play, that exists between the threads of the screw and the nut. When a feed motor reverses direction during contouring, the screw must rotate through that empty gap before the table actually starts moving again. That momentary delay immediately ruins the required 0.0001 inch tolerance. The solution is the recirculating ball screw. The screw and nut feature matching helical grooves, where spherical ball bearings provide the only contact. As it turns, balls travel through the grooves, strike a deflector, and loop back through a return channel in a continuous path. By utilizing preloaded rolling contact instead of sliding contact, internal friction is largely negated, and the physical gap of backlash is entirely eliminated. With the mechanical slop erased, the ball screw ensures every fractional rotation commanded by the MCU results in pure, exact linear displacement of the table. Even with zero backlash, the extreme forces generated by cutting steel can cause the machine frame itself to deflect by fractions of a millimeter. An open-loop control system blindly executes the steps sent to the motors and merely assumes the table arrived at the exact program destination. Industrial CNCs cannot operate on assumptions. They demand an active measuring system to verify reality. This diagram illustrates the feedback system, which relies on highly precise velocity and position transducers. A linear encoder continuously monitors the actual physical location of the cutting tool at any given microsecond. This feedback schematic shows how those exact physical coordinates are sent immediately back to the MCU. The MCU continuously compares the true feedback value against the desired command position, instantly augmenting the amplifier signals to correct any detected deviation. Achieving 0.0001-inch resolution requires this relentless closed-loop paranoia, constantly adjusting and verifying the machine's exact location. When we map all of these disparate components together, the cohesive architecture of the machine is revealed. This system wiring schematic traces the complete life cycle of a single toolpath command. You can follow the routing of the high-voltage, three-phase AC power from the transformer up to the drivers, supplying the brute electrical force. Running directly alongside it is a complex web of low-voltage command data flowing outward from the MCU to direct exactly how and when that brute force is applied. Stripped of its steel casing, a CNC machine is effectively a high-speed data network designed to perfectly manipulate heavy industrial hardware. All of that intricate network complexity exists for one single purpose: controlling the physical reality of cutting metal. Code is decoded by the MCU, amplified by the servo drives, translated into flawless linear motion, and strictly verified by linear encoders. Working together, they enforce a dimensional tolerance of 1/10,000th of an inch, even while carving through solid titanium. This ultimate manufacturing precision is a violent dynamic equilibrium, maintained microsecond by microsecond through the integration of digital code, high-speed electronics, and rigid mechanical engineering.
Thanks for watching and grow every day with just a bit of information. Like, share, and subscribe for more content and learning.